All right, good morning. Today we're going to talk more about asymptotic notation. You'll get the last two of the big five definitions for this topic. We're going to go through some more examples of proving that certain functions are in this case, little o or little omega of other functions. And then it's going to get a bit easier. You'll still need to know these definitions. You might want to memorize them for the quiz. But after this little overview of what little o and little omega are, you'll learn a bunch of tricks that you could use to figure out that functions are in different sets, like big O, big omega, and so on. And it'll more closely resemble how you actually use these in the real world. We'll start with little o. Remember that big O is sort of like less than or equal to. N is in big O of n squared. N is also in big O of itself. That would be the equal part of less than or equal. Little o is like strictly less than. N is in little o of n squared. But n is not in little o of itself. Little o means that f of n grows way slower than g of n. Now, in terms of the definition, it's pretty much identical to big O, except for one quantifier being changed. Instead of there exists an m greater than 0, it's for all m greater than 0. The rest is identical. There exists an n naught such that for all n greater than m naught, f of n is less than or equal to m times g of n. So before, we knew that there existed some constant multiple that we could multiply g by, and then f will eventually be smaller than that. Now, we're making a much stronger statement, which is basically that no matter what constant you multiply g by, f will always eventually be smaller. Little omega is the analogous thing for a function being larger than another, just like how big omega denoted that a function's value was eventually larger or about the same as another function. If f of n is in little omega of g of n, then f of n grows way faster than g of n. No matter what constant multiple you multiply g by, f will eventually be larger than g of n forevermore. Now we've got 3 examples to do. First up, we're going to show that n to the power of 7 plus 8n to the power of 6 is in little omega of n to the 5 plus 1. So of course, if you graphed these, it would look something like n to the 7 is over there, and n to the 5 plus 1 is over here. Eventually, n to the 7 will have values greater than n to the 5 plus 1 for all values of n beyond a certain point. First step is always to do rough work, figure out what values you're going to put into the proof. And for that, it's helpful to rewrite the definition. I won't bother to do this here, just like rewrite this so you know it. And then rewrite the inequality that you're trying to find values to plug into. In this case, n to the 7 plus 8n to the 6 is greater than or equal to m times n to the 5 plus 1. This is kind of gnarly. I've been saying over and over again that we want to simplify our inequalities so that they're easier to compare to each other, and that a complicated inequality, or part of an inequality, is something that has multiple terms. Both sides of this have multiple terms, so we're going to have to simplify both sides. Another detail that I wanted to mention, or honestly repeat, is to pay attention to the quantifiers involved in what you're proving. So in this definition, where we have an arbitrary m, this has to work for all m greater than 0, and then we're finding an n naught such that the inequality works for all n greater than n naught. What this means for our rough work is that we're not going to make any assumptions about m, but we're going to solve for n and give it an expression that is defined in terms of m. So I'm going to start by simplifying the larger side. And remember, I want to find something that is composed of one term and is less than n to the 7 plus 8 times n to the 6. Less than, specifically, because I want it to fit in between the two terms of the inequality and make a sort of chain of inequalities that would end up proving the original one if I simplify it, or if I solve the simplified one. So I think we could just get away with removing most of this term, or most of this expression, because remember, I want to find something smaller than this, and also I want to eventually make it easily comparable to something involving n to the 5. So if I have like something n to the 6 greater than n to the 5, then I would divide both sides by n to the 5, get some lower bound on n, then we'd be done. So I want to make this one term with n to the power of 6. So it's so I can easily solve for n when the other side is n to the 5. So I'm just going to drop n to the 7. You're allowed to do this. As long as n is greater than 1, of course. So if n is greater than 1, then n to the 7 is greater than 1. Actually, I think you don't even need to make that assumption. As long as n is greater than 0, then n to the 7 will be positive, and then n to the 7 plus 8n to the 6 will be greater than or equal to 8 times n to the 6. So that's our simplified big side. Now let's work with the small side. Now here, in order to get an expression that fits between the two sides of the original inequality, I want something that is greater than m times n to the 5 plus 1. So I'm going to use the rounding up trick that's appeared in a few examples previously. So if n is greater than 1, or at least 1, then n to the 5 is at least 1. And thus, we can simplify this to m times n to the 5 plus n to the 5. Which we can simplify to that. So now we have that sort of chain of inequalities that I mentioned earlier. The original big side is greater than our simplified big side, which I'm actually going to simplify a bit further. I know I'm going to eventually be comparing n to the 6, or 8n to the 6 to 2m n to the 5. To make my algebra really, or even easier, I'm just going to remove the 8. Again, you can do this. N to the 6 is positive, so 8 times a positive number is going to be greater than 1 times a positive number. And then this simplified big side is hopefully greater than our simplified small side. And that is definitely greater than our original small side. So now we want to work with just the terms in the middle, because we know this inequality and this inequality are definitely true. So if we show that this inequality is true, or at least find a value of n that works for it, then that'll let us prove the original. By the way, there will be practice questions for this. I keep saying this will make sense with more examples, and eventually there will actually be more examples. I'll get them to you by the time the second assignment drops. For now, worry about the first assignment. Now we're working with our simplified inequality. We've already laid the groundwork to make this really easy. I'm just going to solve for n by dividing both sides by n to the 5. And there you have it, a lower bound for n that should work in the original inequality. Now it remains to prove it. We found earlier that n has to be at least 2m, so we do that. And where'd this 1 come from? I think that was from this step of the rough work. We spell out the consequences of these choices. Then n is greater than 2m, and n is greater than 1, which implies that n to the 5 is greater than 1. And then the last step of the formal proof, the meat of it, is to start with one side of the inequality and then use what you found in your rough work to prove the other side of the inequality. This might be getting awfully repetitive. These will be the last 3 examples of actually proving these from the definitions. Then it'll be your job to do this. So we use a rounding up trick that we detailed here to turn 1 into n to the 5. We get 2mn to the 5. Use the fact that n is greater than 2m to get this. And then, just like we are allowed to just take stuff away to get a smaller expression, you can just add stuff to get a bigger expression. Next up, we're going to do a negation of one of these new definitions. We'll show that n squared minus 8n is not in little o of n squared. That is, even though n squared minus 8n will probably, oh yeah?
Can we solve the above question by taking n raised to 7 common from left side and n raised to 5 from right side?
Probably. Can you say that again?
We have n raised to 7 on left side.
Mhm.
We can take that common out, and we will have 1 plus 8 by n in brackets. On the right side, we have n raised to 5 out, and 1 plus n raised to n by 5.
Wait, are you saying I should do this?
Yes.
Okay. And then something like this? Okay. I don't want to say it won't work, but at first glance, I'm not sure if it will. This resembles the factoring out trick that we did in earlier classes, but crucially, we have addition signs before those fractions. So establishing an upper bound for, or a lower bound for n won't create a lower bound for plus 8 over n. But then that might work for simplifying one of the sides but not the other, just due to the way the inequalities are arranged. There absolutely are many solutions to any given problem. This definitely could work, but it's not the approach I would use. So what are we doing again? N squared minus 8n is not in little o of n squared. Check out the quantifiers. We're going to find a specific m greater than 0 such that for all n naught, there's an n greater than n naught such that f of n is greater than m times g of n. So that means you want to find something that works for this. And because the quantifiers, we're going to show we're going to find a specific value of m because there exists a value of m. And we're not going to make assumptions about n, because even though it says that there exists an n, the constraint on it depends on something that we can't make any assumptions about for all n naught. So we're really not going to bother with much about n. Oh wait, no, we are, totally are. Let's just get on with it. I'm going to solve for n. I want to simplify the larger side. And in this case, I actually am going to use the factoring out trick because I have a larger power minus a smaller power, and I'm trying to find something smaller than that. So now if I suppose that n is greater than 16, then that whole thing gives me a simplified expression with n squared in it. Yes? Oh, I was about to explain. The reason I chose 16 is because with this fraction, we want to find n such that 1 minus 8 divided by n is bounded by some reasonable constant. If you want 1 minus something to be a reasonable constant, a good choice for that something is 1 over 2. So to turn 8 over n into 1 over 2, I just set n to double of 8. 8 over 16. Then I can simplify that. Just like that. 16 was my choice because I sort of saw this 1/2 thing coming. But really, any n that would make it so 1 minus 8 over n is some positive constant would work. You could do, I guess, n equals 80, turn the fraction into 8 over 80, which is 1 over 10. 1 minus 1 over 10 is 9 out of 10. And then the rest of the proof would work very similarly to what I'm doing. None of this is like the one correct answer. It's just one way to get a mathematically correct answer. So now I'm going to solve for m under this simplified inequality. Real simple. M has to be less than 1/2. Now, unless I'm missing something, this formal proof is looking a bit strange because it sets m to exactly 1/2, even though we found that m has to be strictly less than 1/2. Is this a mistake? I don't know. I could be missing something. But my best guess at a glance is that this is just a slight inequality, or just a slight inaccuracy, and letting m be equal to 1/2 minus 0.000000001 would work. We'll just continue on using the value given m equals 1/2. You let n naught be an arbitrary number greater than 0. And then we can choose n greater than n naught. And we let it be the maximum of these two expressions, n naught plus 1, because it has to be strictly greater than n naught, and 17, because it has to be strictly greater than 16. this is just like saying that is the maximum of n naught and 16 plus 1. Those are equivalent. It's a matter of style. I prefer the one that I just wrote down. And then we just spell out the assumptions that we made from our rough work and do the inequality backwards. This less than equal than thing is kind of bothering me. I didn't notice until I was lecturing. I think I'm going to take a look at this later and correct the slide if necessary. But for now, it still works as a good example of the techniques we're using. I think this is our last example of showing these things from the definition. We're going to show that log base 2 of 4 to the n plus 1 is in little o of n squared. Sort of conceptual lesson here is that the log function grows incredibly slowly. We have a whole exponential function in here, which should absolutely not be in little o of n squared. 4 to the n should just like go way faster and exceed n squared pretty much immediately. But taking the log of it just undoes that exponential. And our result is that the log function grows a lot slower than the n squared. Since we're doing little o, we let m be arbitrary and aim to find a specific n naught so that the inequality works for all n greater than n naught. Mn squared, the large side of the inequality, is already nice and simple. So we want to simplify the small side. We want to find an expression larger than that. That involves just n raised to a constant power, maybe multiplied by a constant too. First thing we're going to do is the rounding up trick. If n is greater than 1, then we'll be able to turn this 1 into something we can easily add or sort of combine with 4 to the n. Wahoo! It would work either way. This is rough work, so like you don't have to do it exactly like this. You might end up with some slightly different results in your proof, but it would still work. 4 to the n is greater than 1, whether n is greater than 1 or greater than 4. And then we're just going to manipulate some logarithms. Four to the n plus 4 to the n is 2 times 4 to the n. We use the log law for multiplication turning into addition. And then this part's a bit silly. Four to the n is equal to 2 to the power of 2n. Oh, I keep forgetting these log bases. Once you get far enough into comp sci, the log base stops mattering. And you need to remember at this point it does. Then what do you raise 2 to the power of to get 2 to the power of 2n? 2n, obviously. Then we're not quite out of the woods yet. We want to turn this into an expression that just has one term. Luckily, this doesn't require us to make any new assumptions. If we use our old assumption that n is greater than 1, then n is greater than 1. And we can turn 1 plus 2n into n plus 2n, which is equal to 3n. And what were we doing here again? New simplified inequality. And remember, this is little o, so m is arbitrary, and we're finding a specific n naught, or lower bound on n. So we're going to solve for an inequality of n involving m. And to do that, I'm just going to divide by n on both sides, and divide by m on both sides. Ta-da! So we now have that n has to be at least 3 over m. And we translate that into a value of n naught for our formal proof. Let n naught be equal to 3m plus 1. And let n greater than n naught be arbitrary. I think that plus 1 is used here not to turn a greater than or not to turn a greater than or equal to statement into strictly greater than, but to make sure that n is also greater than or equal to 1, because that's another property of n that we found in our rough work. What?
So we have the baby O, right? Not the big O, but the baby one?
Yeah.
That one's not with the equal to, right?
Okay, excellent question, because the conceptual idea behind this sort of conflicts with what the actual definition is in a way that can be confusing. Little o is like being strictly less than. Log 2 of 4 to the n plus 1 grows a lot more slowly than n squared, but the definition of it still actually uses less than or equal to. No, because the big difference is that big O had there exists an M, whereas this has for all M. Yeah?
Because did we write instead of 3 over m plus 1, can you write the maximum of 3m and 1?
Yeah, absolutely. I really don't know why it uses strictly or less than or equal to in the definition, because if f of n were equal to g of n and f of n were in little o of g of n, then f of n would be strictly smaller than g of n for like n naught plus 1. Since it grows way more slowly, g of n will eventually be strictly greater than f of n. There's probably some like mathematical edge case that some professor way smarter than me thought of and then decided that little o should use less than or equal to. But we're following this definition, and as such, we're using the inequality less than or equal to. Same old stuff as last time. We set n naught based on what we discovered about n during our rough work. And we explain what implications that has for our eventual inequality proof. Then we start at one side of the inequality and use that to arrive at the other side. For the rest of this class, I'm going to talk about some more general properties of asymptotic notation. I think that these are honestly more important than any specific example, because these will sort of help you build your intuition for what functions are in whatever size classes of other functions. So this is one thing that applies. I'll prove it if we have time, but if not, you could just read the proof and then it'll just work. For any constants b greater than or equal to a, greater than 0, n to the a is in big O of n to the b. So that means n is in big O of n squared. And 5 is in big O of n to the 10. N squared is in big O of itself. So these three facts are examples of this general fact in action. Second thing is that for any functions f, g, and h from the integers to the real numbers, all positive, there's a sort of sum rule. Might remind you of calculus stuff. If f of is in O of h and g is in O of h, then f plus g is in O of h. So for example, two n is in O of n. One is in O of n. Be careful about this. This isn't necessarily the number 1, but it's actually the function that returns 1 no matter what n you give it. And you could use those two things with fact B to find that the sum of those functions, 2n plus 1, is in O of n. So basically, proofs are about to get a lot simpler from here. You will have to still know the definition. Oh, yeah?
I was wondering why the domains are positive integers to the positive real numbers.
So that is in order to sort of keep us grounded in computer science. Remember that n is the size of your input. So like if you're doing a sorting algorithm, then n is the number of items in that in the list you're sorting. If you're writing an algorithm to add two numbers, n is the number of bits in those numbers. In both cases, n has to be an integer. You can't have a list with 10.5 items. So that's why we define the domain of these functions as starting with the positive integers. But then also, the outputs can be real numbers because sometimes we have cost functions with things like square roots and logarithms. And now that I think of it, those things should probably output integers as well, because you're never going to have a computer take half of a step. But I guess whoever defined these just sort of considered it unavoidable that things like logarithms and square roots would return numbers that aren't integers, and didn't feel like augmenting their cost functions so that they would like round up to the nearest integer or something. They just left it as, yeah, they might output non-integers sometimes. So say we have these facts, and we want to prove that n to the 4 plus n is in big O of n to the 6. Like I said before, still got to know the definition. This is both for the sake of like understanding what's going on behind the hood, and more practically, because the assignments will involve questions that say you have to use the definition. But for questions that don't say you have to use the definition, you could just say stuff like, well, we know that n to the 4 is in big O of n to the 6 because of this thing. And we know that n is in big O of n to the 6 for the same reason. They're both in big O of n to the 6, so their sum is in big O of n to the 6. Easy. I'm going to spend the rest of class going over the proofs of these properties. But if we run out of time before I go through them, it's no big deal. You could just use them. I would appreciate if you looked at these proofs. There might be like a quiz or exam question to just do this proof yourself, and if you've read this and remember it, it'll be super easy. But I can never say that it's mandatory to read this. So we have B and A, they're constants. B is greater than or equal to A. We want to show that n to the A is in big O of n to the B by definition of big O. And then we just let m and n naught be 1. And then do some trickery with exponents to get the result we want. So since b is greater than or equal to a, b minus a is a positive number. Because b minus a is a positive number, n to the power of ba, nba, it's like the basketball. That is greater than or equal to 1. And then we could multiply by both sides by n to the a. I don't think we need to go into this much deeper. This proof was probably derived by a bit of trial and error, some rough work that I wouldn't be able to reproduce. There probably won't be a quiz or exam question that is based on reproducing this proof. If there is, I'll give you all warning in advance. Now, this is the proof of that sum rule we found first, or we found earlier. We assume that f is in O of h and g is in O of h. This is what that means by the definition. And based on the m1, n1, m2, and n2 we'll show that there exists m3 and n3 such that f of n plus g of n is bounded below by some constant multiple of h of n. That is, f of n plus g of n is in big O of h of n. It's a lot of algebra. The moral of this story is that we just let m3 be m1 plus m2 and n3 be n1 plus n2. And then it sort of just works by the distributive property. m1 times m2 times h of n is equal to m1 times h of n plus m2 times h of n. And we already know that f of n is less than m1 times h of n, and g of n is less than or equal to m2 times h of n. So like I said, distributive property, it just works. So here's the cutoff for the quiz. Actually, no. Here's the cutoff for the quiz. For Friday, you'll want to maybe not memorize, but have a good understanding of all the definitions, like big O, big omega, little omega, and big theta. You don't necessarily need to memorize them, but if you do memorize them, the first question of the quiz will be super easy. The second question of the quiz, I haven't decided yet, but will probably be something like the examples I did today, which is proving that some functions are related to each other in some way from the definitions. So that's all for today's class. If you have any questions, let me know. Good luck on assignment 1 and the next quiz.